Okay, good morning all of you. And I think a few of you attempted the assignment that is given, but I strongly recommend all of you to start working on the assignment, strictly following whatever procedure that is given in Annexure A of IS 10262-2019 version of the code. Just before we proceed, I just want, because something I left in the last class, I just want to bring to your attention that one, and then we'll proceed further, okay? In the last class, I have not discussed or I have not mentioned this one. If you refer Annexure A of IS 10262-2019 version of the code, mixed design code, there is some correction for air content in the, depending on the aggregate size. So that once you go through the example, you will understand it. So I strongly advise each of you to strictly follow the code and then attempt it as soon as possible. Okay, here just read this one. Approximate amount of entrapped air to be expected in normal. And here we are not adding any special air entrained admixtures, okay? So approximate amount of entrapped air to be expected in normal.
Sir, you have not started screen sharing.
One second. Sorry about it. Okay, this is what I'm mentioning. Last class, I did not bring to your attention this table, which is table 3 of IS 10262-2019 edition of the code. Okay, so this is what code is saying: approximate amount of entrapped air to be expected in normal concrete, and in special situations, we are going to put some admixtures to actually make it air entrained. But here under for normal concrete, what is the amount of entrapped air that you can make use of in your design, mixed design, that is given here, which is actually going to be a function of your nominal maximum size of aggregate. Okay, what is a percentage? And if you see annexure A problem, worked out problem in the code, 2019 edition of code, for nominal maximum size of 20 mm, 1% is taken, and it is all self-explanatory. You go through the procedure and follow the same thing, okay? And you can even read this one. These are the codal recommended values when you don't have any data, okay? The actual amount of air content can also be adopted during mix proportioning if the site data for similar mix is available. At least five results. Okay, if site data is available, then you can make use of it. Otherwise, this is a approximate air content that you can use in your mix design. Okay. So anyway, you attempt the problem, then we'll discuss further if you have any questions on the design mix issue. So now let's go further and make a note of other things. So by the end of today's class, you will be getting an idea about what is the stress strain curve that we'll be using in our reinforced concrete design for concrete. Okay, stress strain curve, design stress strain curve for concrete, which is prescribed by the code. So before that, we need to make a note of few points or a few other properties which we require. So we know how to get the compressive strength, characteristic compressive strength, which is denoted with FCK. Okay. So similarly, we also need to know what is tensile strength. Okay. So flexural here, tensile strength. The flexural strength of concrete is generally referred to as tensile strength. Is required to compute the onset of visible cracks in a concrete structure under flexure. Okay, suppose you take a simply supported beam, and from your mechanics of materials, you learn that bottom fibers are going to be in tension, top fibers are going to be in compression if it is subjected to sagging moment. So bottom fibers are going to be in tension. If concrete is there, the beam is consisting concrete, so the concrete which is the bottom portion, it's going to be under tension. Okay, so what is the once the tensile stress exceeds certain value, you are going to see visible cracks. So what is that value? It depends on the strength of tensile strength of concrete. That is what is mentioned here. The flexural strength of concrete is generally referred to as tensile strength required to compute, and it is required to compute onset of visible cracks in a concrete structure under flexure. Okay, for computation of load factor under cracking, knowledge of the flexural strength is required. Anyway, we'll see this. Okay, even if you don't understand this sentence at this stage, it's okay. So let's go further. According to IS 456-2000, tensile strength of concrete can be computed from. So far, what you learned how to calculate characteristic compressive strength. Can we estimate tensile strength of concrete from that? Code is giving an equation. Okay, and also if you recall in earlier lectures I mentioned, you can even take it as 10% of the compressive strength. Okay, so anyway, IS 456-2000 is giving this equation to calculate the flexural strength. Flexural strength here, it is actually denoted with FCR. Okay, it's like the strength or the value of stress which when the concrete starts cracking or something like that. That's why it's denoted with FCR. So flexural strength FCR is equal to 0.7 root FCK in Newton per mm square. FCK is characteristic tube compressive strength of concrete. Okay, and where it is given in IS 456-2000, I will show you that it's given page 16 of IS 456. Okay, here flexural and splitting tensile strength shall be obtained as prescribed in IS 516. Flexural strength, how to obtain? It is given in IS 516, and splitting tensile strength, it is given in IS 5816. Okay, even IS 516 is talking about splitting tensile strength. Okay, so flexural and splitting tensile strength shall be obtained as described in IS 516 and IS 5816 respectively. When the designer wishes to use an estimate of the tensile strength from the compressive strength, the following formula may be used, which is what we just discussed. Okay, so where exactly this is used, where exactly this flexural strength is going to be used, we'll see in a while. I'll for completeness, I'll show you that as well. Okay, so what is this splitting tensile strength apparatus, how it looks like, and how this flexural tensile strength test apparatus is going to look like, or test setup is going to look like, that is shown in these figures. So this is apparatus for split tensile strength. You need to cast concrete in the form of a cylinder. That cylinder is going to be placed between these steel plates or steel loading piece. Okay, and it's going to be loaded, and then it's going to split. It's going to split into two parts. This cylinder, and the strength or the load which corresponds to that is going to be your indication of your splitting tensile strength. Okay, and similarly, so this is for splitting tensile strength, and similarly this is flexural test setup and corresponding specimen. The details, what is the dimensions of these specimens? If it is split tensile strength specimen, what is the dimension of that cylinder? Everything is given in code. Okay, IS 516, IS 5816. So this is how you will be determining the tensile strength of concrete. And next one is important properties, modulus of elasticity. Modulus of elasticity of concrete, which is significantly influenced by the type of aggregates used, type of cement, mixed proportions, is an important property required for computation of deflections of structural concrete members, which forms an important limit state in the design of concrete members. Anyway, it is this modulus of elasticity is an important property where we require deflection calculations. And if you recall your mechanics of materials, you know the deflection formulas for various loads and various boundary conditions. Here the deflection formulas are given, slope, deflection and other things are given. Maximum deflection, all these values are given for cantilever subjected to point loads at different locations, and also various types of loadings. Okay, similarly you have all these formulas for simply supported different boundary conditions. Okay, different boundary conditions of the beam, you have all these formulas. So if you see any of these deflection formula, you can see in the denominator you have EI. EI is nothing but flexural rigidity of this particular beam. So E is Young's modulus. So this is where we will be using that Young's modulus of concrete for estimating the deflections, for calculating these deflections, and which will be used in limit state. Okay. Anyway, we'll see what is that limit state and other things later. So how to estimate this modulus of elasticity in the absence of test data? Actually, IS 516 is giving you a procedure to estimate or to experimentally determine this modulus of elasticity. But if you want, if you know concrete compressive strength, how to estimate the modulus of elasticity from that is given in this IS 456. IS 456 2000 is giving that. Okay. So in the absence of test data, the modulus of elasticity of concrete is normally related to compressive strength and is computed by empirical relation. Okay, given here. EC is equal to 5000 root FCK. EC is equal to 5000 root FCK. EC is a short-term static modulus of elasticity of concrete expressed in Newton per mm square. Newton per mm square. Okay. EC is a short-term. It's a short-term static modulus of elasticity of concrete expressed in Newton per mm square. So what is this static? What is this static modulus? If you see IS 516, it is also giving you test procedure for determining the dynamic modulus of elasticity of concrete. But what we are talking here is static modulus and also short-term. Okay, I want to emphasize this word short-term at this stage, but we'll see before end of today's lecture. You will see what is the long-term modulus of elasticity. That also we'll see. Okay, which is going to depend on creep and other things. We'll see that. Okay, FCK is characteristic compressive strength of concrete expressed in Newton per mm square. So this is also given. This entire thing is also given in IS 456. Page 16, you can see that here. Modulus of elasticity of concrete is given by this one. And please note that here, one more thing. Code is giving some additional information. Actual measured value may differ by plus or minus 20% from the values obtained from the above expression. Okay. So this is an approximate value. Approximate modulus of elasticity, short-term static modulus of elasticity.
Okay, let me just add something at this stage. See, please note both these equations are actually empirical equations. Means someone has done some test and did a curve fitting and found that both the flexural tensile strength and the modulus vary somewhat parabolically with respect to compressive strength. Do not consider notational homogeneity in these equations. Sometimes I find that students say that FCK is Newton per millimeter square. If I take square root of that, then the unit of EC will be square root of Newton per millimeter square. No. FCK is Newton per millimeter square, as well as the modulus or the strength is also Newton per millimeter square. The dimensional homogeneity is not applicable in this type of empirical equation. Okay.
Okay, let's proceed further. Okay. And shrinkage of concrete. Ingredients of concrete and environmental conditions like temperature and humidity influence total shrinkage of concrete. Water content in concrete significantly affects shrinkage. IS 456-2000 recommends total shrinkage strain as 0.303 in absence of test data. Drying shrinkage in plain concrete may result in surface cracks. We'll see what is that. Okay. So drying shrinkage is going to result in surface cracks, or it is going to manifest in the form of surface cracks. And shrinkage of concrete also influences deflection of reinforced concrete members. And at this stage, so let me read once again before I proceed. Shrinkage of concrete also influences deflection of reinforced concrete members. So let's see about this. So free shrinkage. So you have imagine this is some cube or some kind of rectangular shaped concrete. Concrete. You casted this kind of concrete. Okay, before shrinkage, let's say these are how the dimensions looks like, and after shrinkage, this is what is going to happen. Okay, and this is what is free shrinkage. You are not restraining. You are not putting any restraints on the boundaries of this concrete whatever this member. Okay, so it is what is free shrinkage, causes volume change, but no stresses will be developed. No stresses will be developed, but there is going to be strain. There is going to be strain, but no stresses will be there because no restraint is there. It can actually shrink, or it can take any shape it wants. So no restrictions are there. So no stresses are going to be developed. So now what happens if I have some kind of restraints? So these two ends are some kind of restraint is placed. Let's say fixed. These two edges are, or these two ends are fixed, this end and this end. So restrained shrinkage creates stresses which may cause cracking. Okay. And this is how the cracks are going to appear because of this shrinkage. So parallel cracking perpendicular to the direction of shrinkage. So the member is going to shrink in this direction. The cracks are going to be approximately perpendicular to that direction. Okay. And so let's see what IS 456 is, where it is mentioned in IS 456. That is mentioned right below the Young's modulus of concrete. So the details, whatever we just discussed, that is there here. If you want, let's go through it once again. The total shrinkage of concrete depends on constituents of concrete, size of the member, and environmental condition. For a given humidity and temperature, total shrinkage of concrete is most influenced by the total amount of water present in concrete at the time of mixing. Keep that in mind. And to a lesser extent by cement content. Okay. In the absence of test data, the approximate value of total shrinkage for design may be taken as 0.303. Okay. Where this modulus of elasticity is used, where this shrinkage coefficient is used, all these things we will see in a while. So now let's go further to creep. Inelastic time-dependent strain developed in a concrete member under sustained loading is referred to as creep. It is inelastic and time-dependent. Okay. So inelastic time-dependent strain developed in a concrete member under sustained loading is referred to as creep of concrete. And creep of concrete is influenced by cement content, water-cement ratio, aggregate cement ratio, temperature and humidity, size of the structural member, type of loading, and period of loading. Okay. So in IS 456, how to take care of this creep? It is given in terms of creep coefficient. Let me close this one. Creep coefficient. Under this section 6.2.5, creep of concrete. Okay. Let's read this for completeness. Creep of concrete depends in addition to factors listed here. That is nothing but the constituents of concrete, size of member, and environmental conditions. And in addition to that, it also depends on the stress in concrete, age at the loading, duration of loading. As long as stress in concrete does not exceed 1/3 of its characteristic compressive strength, creep may be assumed to be proportional to stress. Okay, creep strain is going to be proportional to stress as long as the stress is not exceeding 1/3 of the characteristic compressive strength of the concrete. In the absence of experimental data, detailed information on effect of the variables, on the effect of these, some of these whatever size, constituents, size of the member, environmental conditions, stress in concrete, all these parameters, all these variables, in the absence of detailed information on the effect of all these variables, ultimate creep strain may be estimated from the following values of creep coefficient. What is creep coefficient? It is nothing but it's a ratio of ultimate creep strain to the elastic strain at a given age of loading, at the age of loading. So creep coefficient is ultimate creep strain, ratio of ultimate creep strain to the elastic strain at the age of loading. So it's going to depend, this ratio is going to, or this creep coefficient is going to depend on the age of concrete. Okay. Anyway, it's also mentioned for long span structure, it is advisable to determine actual creep strain likely to take place. That is different issue. Okay. So now, depending on the age, what is the creep coefficient that is given in this section 6.2.5.1. At different ages, what is the creep coefficient? So what is that ultimate creep strain to the elastic strain, that ratio? You can see here at early age, creep coefficient is larger. As the age is gained, as the member gains age, creep coefficient is going to come down. Okay, so we'll make use of all these. Okay, and let's also see how this creep is going to vary with respect to the time. So this I mentioned to you here, inelastic time dependent strain. Inelastic time dependent strain. What is the meaning of that? That is shown here in this schematic. Here deformation is plotted in the vertical axis. Deformation is plotted on the vertical axis, and you can say this horizontal axis as time. Okay. So now a member is already loaded. A member is already loaded. So immediately after load is applied, this is the deformation. And that load is kept for some time. As the time progresses, deformation increases at the same load, at that load, whatever constant load you are applying. This is instantaneous deformation. And as time progresses, this is how that deformation is going to increase. Okay. And then let's say at this point of time, you remove that load. Immediately, some portion of the deformation you are able to recover. So that is what is elastic recovery. And rest of the portion is going to be asymptotically or exponentially is going to decay. And it's going to match with the deformation that you have at the initial point, or initially at time 0 you applied load, and immediately there is some deformation, so it's going to match with that deformation. So this is how the creep behavior is going to be. Okay, so that is what is mentioned here: deformation of hardened concrete under load. So this is what inelastic time dependent strain. Okay, so this figure explains you that one. And anyway, we already noted all these things, IS 456. Okay, so let's go further. Thermal expansion of concrete. The coefficient of thermal expansion of concrete is influenced by the type of aggregate used in the concrete, and it is required for design of structures like chimneys, water tanks, silos, etc. Okay, and depending on the aggregates, depending on the type of aggregate, IS 456-2000 is giving you coefficient of thermal expansion of concrete. Depending on the type of, at the time of discussing about coarse aggregate, I showed you some of the different types of the minerals or the stones that can be used as an aggregate. Some of these again repeated here: quartzite, sandstone, granite, basalt, limestone. Depending on what is going on or what is going into the concrete, what type of aggregate is going to into the concrete, coefficient of thermal expansion of concrete is going to depend. Okay, so this is also given in IS 456-2000, page 16. Page 16 is giving you that one. Okay, so now let me, you already noted what is Young's modulus or what is tensile strength. You noted first as a part of today's lecture, you noted what is flexural strength or tensile strength. You also noted Young's modulus of short-term static Young's modulus of elasticity of concrete. That also you noted. Shrinkage coefficient, what in the absence of data, what is the value that code is recommended, that also is noted. And the creep coefficient for different ages, that is also noted. Okay, so now let's see where these are all used. Where these are all used. Just let me show you. Let's go to IS 456-2000. Annexure C. Annexure C is giving you, we'll go in detail later. Okay, at this stage I want to show you exactly where we are going to use. So I showed you, you need to go back to your mechanics of materials, and for different support conditions and different loading conditions, what is the deflection that is going to be there at the different locations of the beam, and also what is the maximum deflection that you will be able to estimate using whatever you learned as a part of your mechanics of materials or as a part of your structural analysis. So that is what is summarized here for few cases. So let's see this one. Cantilever subjected to point load at the tip. Maximum deflection is given by this one. Okay, let's assume this is this beam, whatever this beam, this cantilever beam, let's assume it is made of reinforced concrete. Let's assume this is made of reinforced concrete. Then how to estimate this maximum deflection? So here I have I is nothing but moment of inertia, and because the concrete beam, whatever reinforced concrete, whatever we are saying, that is a composite material. It's a if it, suppose if this beam is like a wooden beam having a rectangular cross section, and you know how to calculate this moment of inertia. But this beam is reinforced concrete beam. This beam is reinforced concrete beam. So you also have concrete as well as steel. So in that case, how to estimate this I, moment of inertia? This annexure C is giving you how to calculate that. We will go in detail at the time of actually you making use of it. But I just want to bring to your attention here, there is something called I effective. I effective is nothing but effective moment of inertia. Effective moment of inertia. Some expression is given here. Some expression is given for effective moment of inertia in IS 456, Annexure C, page 88. Page 88, IS 456 2000 is giving you an expression for effective moment of inertia. And if you see this one, in this there is something called MR, M subscript R. M subscript R is there. That is nothing but cracking moment. Cracking moment. So let's assume I have this cantilever beam here. I have this cantilever beam. I'm applying a point load at the tip. As the load increases, bending moment is also going to increase. Okay. And at a particular value of load, first crack is going to be visible, or first crack is going to be formed. Because this is reinforced concrete beam, concrete is weak in tension, okay? And so obviously the fiber, extreme fiber, in which the tensile stress exceeds whatever flexural strength that expression is giving. Just now we have noted from IS 456 0.7 root FCK. That is the flexural strength. Once tensile strength exceeds that, crack is going to be formed. So I want to know at what load crack is going to be formed, or at what moment crack is going to be formed. So that cracking moment is what is this one. Cracking moment is MR. MR is given by FCR multiplied by IGR divided by YT. And if you go back to your simple bending, you go back to your mechanics of material, whatever you have studied, okay, theory of simple bending, you must have learned a formula. M by I is equal to F by Y is equal to E by R, which is coming from Euler's theory of simple bending. You make a note of it on your paper. F divided by I is equal to M divided by Y. And you rearrange it. M is equal to F multiplied by I divided by Y. So that is what exactly this one. FCR is nothing but what is the stress corresponding to or the tensile strength, or it's also called modulus of rupture of concrete. FCR expression you already noted, it is 0.7 root FCK, that is tensile strength, and it is also called modulus of rupture. Okay, so that is FCR. And whatever formula that you learned in your theory of simple bending, I is replaced here with gross. IGR. IGR is nothing but gross moment of inertia of the section. And this gross moment of inertia is going to be function of this effective. Okay, this I effective is going to be lying between the moment of inertia for fully cracked section. We'll see all this later. Okay, anyway, for calculating this cracking moment, you require this information. FCR, whatever you learned just now, tensile strength of concrete, and IGR is the gross moment of inertia of the particular section. Y is the distance of the point from the neutral axis. where you want to find this if you are interested in the stress at a particular point, what is the distance of it? But here we are interested in cracking moment or the maximum moment, so that y is going to be yt is going to be the distance to the extreme fiber in tension. Yt is the distance from centroidal axis of the gross section. Anyway, forget about all this, we'll see later. Okay, yt is distance from centroidal axis to the extreme fiber in tension. That is what is yt. So this is where we'll be using that FCR, whatever we noted, 0.7 root FCK. Okay. Anyway, we'll come back to this at a later stage, more detail. Okay. So now you also learned about creep coefficient, or sorry, shrinkage. Shrinkage coefficient you already noted. What is that? So that is going to be used here. That shrinkage, deflection due to shrinkage in the calculation of this, we'll be using that one. You can see here. Epsilon CS. Epsilon CS is the ultimate shrinkage strain of concrete. Epsilon CS is the ultimate shrinkage strain of concrete, which is given in page 16 of IS 456 2000. And what is that value? You need to remember all these values. Okay, so few of these at least you need to remember. 0.303. That is what is epsilon CS, shrinkage strain. Okay, so this is where we'll be using. So for the calculation due to shrinkage, deflection calculation due to shrinkage, we'll be making use of that shrinkage strain, whatever we noted just now. And in addition, we also noted what is the creep coefficient. Creep coefficient. And also, I emphasized whatever modulus of elasticity of concrete that we noted, 5000 root FCK in Newton per mm square. That is short-term modulus of elasticity. And here you can see effective modulus of elasticity. Means if you want long-term value of modulus of elasticity, that is going to be a function of your creep coefficient. So short-term modulus of elasticity EC divided by 1 plus theta. Theta is creep coefficient. Just now we have seen in page 16 of IS 456. For different ages, what is the creep coefficient? For 7 days, what is the creep coefficient? What is the creep coefficient for 28 days? What is the creep coefficient for 1 year? Okay, just let me show you. So this is where exactly we'll be using that creep coefficient information. So what is this for deflection due to creep? So we'll be making use of all this: tensile strength, whatever we noted, modulus of elasticity, and whatever shrinkage, whatever value of strain we noted, 0.303, and also shrinkage, creep coefficient for different ages of concrete, whatever we noted, will be all those, that information will be using in the deflection calculation. Okay. Anyway, we already durability consideration. From durability consideration, we already noted all these things, but for completeness, let's go through this quickly. Concrete is durable if it performs satisfactorily without deterioration when exposed to different types of exposure condition during its service life. The main factors influencing the durability are type of environment, type of quality of concrete, cement content, water cement ratio, workmanship, cover to the embedded reinforcement, shape and size of structural members. And we also made use of all this in our design mix as well. Okay, and also we noted all these points. Okay, so now let's go to one more aspect: freezing and thawing. And this is where we'll be using some special admixtures for entraining this air. And what is the percentage? Let's go through this. Under severe exposure conditions, when concrete is subjected to freezing and thawing, it is preferable to use air-entrained concrete for grades less than M50, air-entrained concrete obtained by using air-entraining admixtures is ideally suited to resist destructive effects of freezing and thawing. IS 456 2000 recommends the following percentages depending on the maximum or nominal maximum size of aggregate. Anyway, we'll make use of it when it is required, but all this is given in your IS 456. Page 16, here, page 18. Page 18 is giving you that. Freezing and thawing. Okay. So let's quickly proceed further. And sulfate attack, we already noted all this. So I don't want to emphasize it once again here. So let's go to the next one. Fire resistance, corrosion, cover requirements of RCC members. And table 1616A of IS 456 2000 is giving you cover requirements from fire point of view and from corrosion. Corrosion is a durability point of view. Okay. And before we go and see table 16 and 16A, we just note down this one. Fire resistance rating typically means the duration for which passive fire protection system can withstand a standard fire resistance test. So passive fire protection system. So how we are protecting this steel, because steel is going to melt if temperature is very high because of this fire. So we want to protect that steel. So passive fire protection system. We are going to protect the steel by providing some cover. So that is what this table 16 or 16A of IS 456 is giving. One is for fire, another is for corrosion or durability point of view. Okay. So let's read this. This can be quantified simply as a measure of time, or it may entail a host of other criteria involving other evidence of functionality or fitness for purpose. Okay. Anyway, as a passive fire protection system, we are going to adopt some minimum cover, and that cover is given. What is that value of cover? Depending on the fire rating, that is given in page or table 16, and let me show you that. (16) and 16A. Here. Now 16 is giving cover requirements from durability consideration. That is nothing but corrosion. Okay. Nominal cover to meet durability requirements. So let me magnify it. Or maybe. So you already know these exposure conditions. Under these exposure conditions, what should be the cover? Concrete cover. That is given here. Okay. We'll be making use of this information when we actually design. Similarly, table 16A is giving nominal cover to meet specified period of fire resistance. Specified period of fire resistance. Fire resistance rating or fire resistance is actually given in terms of hours here. H is hours. Half 30 minutes, 1 hour, 1.5, 2 hours, 3 hours, 4 hours. So if you want your structural member to withstand fire for safe escape of all the occupants, so what should be the minimum cover? That is given in this 16A. Nominal cover to meet specified period of fire resistance. Okay. Anyway, when you do the design, depending on the situation, you need to, before you give your prescription, you need to cross check whatever cover you are recommending, whether it is complying with the codal requirements or not. So at that time, you need to once again cross check all this. Okay. So let me proceed. One more thing, bond strength. Bond strength is nothing but you have whatever we are going to talk, or whatever we are talking is about reinforced concrete. So steel is embedded in the concrete. So we are interested in the bond between the steel and the concrete. So the shear stress at the interface of reinforcement bar and concrete develop. So it is shear stress. It is shear stress at the interface of reinforcement bar and concrete developed to resist the slippage of bar relative to the surrounding concrete. And where this value is given in the code. So it depends on, first of all, it is the shear stress at the interface of reinforcement bar and concrete. So it depends on the grade of concrete, whether it is M20, M30, or what type of that. And also it depends on the reinforcement bar, the surface of the reinforcement bar. And we'll see in tomorrow's lecture or next lecture, you will be seeing details about reinforcement bar. Reinforcement bar can be plain bar, or you can have some kind of deformations, or it's also, they're called ribs on the reinforcement bar. Okay, ribbed bar. So whether it's plain bar or ribbed bar, and what grade of concrete, the shear stress is going to depend on that. And that is given in IS 456 in page 43. Here, what is that bond stress or bond strength? So it is a shear stress that is going to be developed at the interface between the reinforcement bar and the concrete. So let's say you have some beam, and you already, that beam means already a certain grade of concrete is adopted and a certain type of steel is adopted. So both are actually fixed. So now what is the bond strength? How to estimate that? You can make use of this table. So depending on the grade of concrete, and you read this title, this is a bond stress in the limit state method. We'll just make a note of it about this later. The design bond stress for plain bars in tension, which is function of grade of concrete, and also the type of bar. It's a plain bar, no deformations or no rips on the bar. And so as we have seen earlier, whenever some table is developed for certain case, some corrections will be applied for some other cases. If it is deformed bar, code is saying you increase these values by 60%. And here, assuming the bars are in tension, these are the values that are given. But suppose your bar is in compression, then increase this bond value, this stress or bond stress values by again 25%. So if you have a ribbed bar or deformed bar, first unit increase by 60%, and whatever value you get, if that bar is in compression, you increase it again by 25%. Anyway, we'll make use of it. I want to show you few of the information which is required later. Okay. So that is another important thing, this bond strength. Now coming to, before we close this class, we need to note down what is stress strain curve for concrete. What is the design stress strain curve for concrete? So that is where we are heading. The knowledge of stress strain curve for concrete is essential in developing analysis and design procedure for concrete structures. And next figure, we'll see that figure presents typical stress strain curves for, typical stress strain curves obtained from concrete cylinders having height to lateral dimension of 2. So concrete, some tests are conducted on concrete cylinders. What is the dimension? What is a dimensional ratio? The height to diameter. It's a cylinder, so lateral dimension is going to be same everywhere in any direction. So height to diameter ratio of 2. So typical stress strain curves obtained from concrete cylinders having height to lateral dimension ratio of 2 loaded in axial compression in a test conducted under uniform rate of strain. So under these conditions, some tests are carried out, and the curves which we are going to see are based on those tests. And let's see these curves. Sorry. So this is a curve. Okay, 3 curves are shown here. Stress versus strain. Stress strain curves for concrete, cylinder specific. And some important observations from this figure, we'll make a note of it. Okay. And you can see here the peak, the maximum, the strain corresponding to the maximum value of stress. This is the stress for these different curves are different strengths of concrete, different grades of concrete. For different grades of concrete, these different curves are there. Irrespective of whichever curve, you can see here the peak value of stress is almost for every case. It is the strain corresponding to that is matching with 0.202. And I told you these curves are for different strengths of concrete. The upper curve is for higher strength concrete, the bottom one is for the lower strength concrete. As the strength of concrete increases, the steepness of this initial portion is going to it is going to be steeper. So these are some of the points which we'll be noting here. The curves are almost linear up to about half the compressive strength. That is the first point. So the peak compressive strength is, let's say, this peak value is this. It's almost linear up to at least half of it for all these. Okay. And the strain at maximum stress is approximately 0.202. Higher the grade of concrete, steeper is the initial portion of stress strain curve. And also sharper the peak and lesser the failure strain. Let's note down that. As the grade of concrete is increasing, as the strength of concrete is increasing, this peak is becoming sharper, and also the strain. You can see a strain at the ultimate is smaller for this, or it is lesser for this. That is what it is noted here. Higher the grade of concrete, steeper is the initial portion of stress strain curve, sharper the peak, and lesser the failure strain. Okay. And here the test is conducted under uniform rate of strain. Why this point is emphasized? If you conduct test under uniform rate of stress, you will not be able to capture the descending portion of the stress strain curve. Descending portion of the stress strain curve means after the maximum is reached. If you are adopting constant stress, okay, or uniform stress loading or uniform, there are two types of tests. One is strain controlled, another is stress controlled, or one is load controlled, another is displacement controlled. And if you are able to control only the strain, you will be able to capture this portion after the peak. That is what that two sentences are mentioning here. Okay, this sentence is mentioning about that. Anyway, let's note down few more salient points on this curve, and then we'll see what is the design stress strain curve for concrete, which is given in IS 456-2000. Okay, so from these curves, whatever we just noted is, as the grade of concrete, as the strength of concrete increases, this is becoming steeper, and also peak is becoming sharper, and the failure strain is actually becoming lesser. And also, irrespective of whatever strength of concrete, almost all the curves are peaking the value, the stress value is peaking at a strain corresponding to 0.202. So with this, we can actually get an idea about design or stress strain curve that we need to adopt for design. So for that, what are the requirements? An equation representing stress strain curve completely should satisfy the following conditions. At F is nothing but your stress, epsilon is nothing but strain. At the zero stress, zero strain, the slope is equal to Young's modulus of concrete. At the maximum stress, strain is going to be the maximum, and your slope should actually, it should be zero at this point. Slope should be zero at this point. And also the stress at the maximum or failure, when the specimen fails, or when stress reaches its max failure value, strain should actually reach its ultimate strain value. That is what this is. So something which actually satisfies all this, we can make use of that kind of thing as a design stress strain equation or the stress strain curve. Code is giving you directly stress strain curve, design stress strain curve. Okay. The equation satisfying all these conditions is used in the limit state design method. Let's see that. Okay, limit state design method, or what is the stress strain curve that is given in the code. Let's see that. So that is actually given in page 69.
Professor, now it's not 12 o'clock. Today we can wind up.
Okay, I will stop here after this. Okay. So whatever points we noted, based on that, this is what code is specifying. Design stress strain curve for concrete. Okay. And it's given in page 69. And it is actually function of your compressive strength of characteristic compressive strength of concrete. Okay, tomorrow we'll continue on this. And now it's open. You can ask any questions quickly, 1 or 2 questions. Or otherwise, we'll meet tomorrow. Tomorrow we can have discussion on this. Okay, Professor Amlan?
Yeah, I think today is fine, because tomorrow again we need to go through the stress strain curve. This is an important topic, and let's start again tomorrow.
Okay, thank you.